Welcome back to our video series named Materials Phenomena in Nuclear Environments. So in the last video we talked about two cases where the neutron hits an iron nucleus. It hits the iron nucleus, and this is the second case. We talk about the iron nucleus having this much momentum. Now how much kinetic energy will it have, and will the atom be displaced? Now this is what this video is about. So we want to find out the kinetic energy, and this is the appropriate expression for kinetic energy using the momentum as reference. So all we have to do is to substitute this into this equation, and by doing that we just square everything here. We square everything here and then we substitute in. So PFE squared is this whole messy thing here, and 1 over 2 MFE is on the right hand side here. So we want to simplify this expression. Then we will have 4 into MFE, because this is 2 squared. So 4 into MFE. 4 into MFE over Mn plus MFE squared. This is the bottom. Okay, so this 2 will come to the bottom here, and MFE squared will be divided by MFE to give MFE. Okay? So of course I could write it put a neater expression by cancelling this 4 and 2 and leaving the 2 on top. But yeah, I was just writing over some old papers after, careless mistake. But anyway, the mathematical expression is pretty much the same. So Tni equals to 4Pni squared over 2 times the mass of the neutron. So it goes to 2Pni squared over Mn, in other words. So what is Pni squared? And how can we relate? Oh, okay. I think there's a mistake here. Never mind. So, regardless, what we have is TFEF, which we want to find out, and we have it in terms of this expression we are talking about here. So this expression I'll just simplify as 2MFE over Mn plus MFE squared into Pni squared. Okay? So what is Pni squared? Pni squared, okay, Pni squared over 2Mn equals to Tni. Okay, so just ignore this part here. Okay, so this is the standard expression. Now all we have to do is just substitute this Pni squared into this expression here. So I'll just rearrange this equation by bringing 2Mn to the right hand side, and I'll just substitute this into this equation. By doing so, we find that, okay, by doing so we find that, okay, this 4 over 2, that's just 2, yeah? So 2Mn into Tni, so that is the Pni squared, and you multiply into this 2MFE over Mn plus MFE squared, which is this term. So I'll just multiply this, and all we are left with is TFEF equals to 4 into Mn into MFE over Mn plus MFE squared into Tni. Now let's substitute some numbers so we can actually find out if this atom is displaced, this iron atom is displaced. So what's the typical value of the kinetic energy of the incoming neutron? That's Tni. Usually in a fission reactor, we find neutrons at about 1 MeV, and this is these are talking about fast neutrons. Okay, And what are the values of Mn and MFE? Mn is 1 atomic mass unit and MFE is 56 atomic mass units. Now we can use kilograms or atomic mass units. It doesn't really matter for this case because the units will cancel out. So let's substitute these to find whether our iron atom is dislodged. So if I substitute 4 into MFE into Mn, so this is the mass of the neutron, the mass of the iron atom. So 4 into 56 times 1 over 56 plus 1 squared. That's the mass of the iron atom, or mass of the iron nucleus, plus the mass of the neutron. We square it, times 1 MeV. That will give us this expression, 4 into 56 over 57 squared. And after we punch in the calculator, it should give us about 0.0689 MeV, or this number here. Okay, if you can't see it, never mind, just look at the one here. So this is talking about the maximum kinetic energy that the iron atom can get from a 1 MeV neutron. So what is our displacement energy? ED? Okay. ED is about 25 or 25 to 35 electron volts. But even at the upper limit, this is 0.0689 million electron volts. This is way more than 35 electron volts. So in this case, the atom is probably dislodged or displaced. And we should also note that yes, this is the maximum case where the neutron is recoiled or scattered 180 degrees backwards, and the iron atom is pushed forward with this amount of kinetic energy. We should note that every time the neutron knocks off or knocks onto an iron atom, we call this iron atom, which the neutron knocks onto, the primary knock-on atom, also known as the PKA. So anytime I'm going to talk about PKA in future videos, we are actually talking about this primary knock-on atom, where the neutron has actually knocked onto it directly. Now this is one of two extreme cases, of course. The other being that the neutron is not deflected at all. So this is the upper limit of the kinetic energy. So T of the iron after collision, the kinetic energy of the iron after the collision at maximum value, that is 0.0689 MeV for the 1 MeV neutron. So on average, of course, you won't have this amount of kinetic energy being transferred to the PKA, or the primary knock-on atom. Statistically speaking, we have about half of this kinetic energy being transferred to the PKA. So how much energy is that? That's about 0.03447 MeV. That's still a lot of kinetic energy, and the atom is definitely going to be displaced. Additionally, we want to note that this primary knock-on atom has a lot of energy. So how much is that if we are talking about it? Yep, 0.03447 million electron volts or mega electron volts. Okay, that's about 34472 eV. Now, considering that the displacement energy is about 35 eV at max for the iron atom, we note that even this primary knock-on atom can go on to cause a lot of damage. So see, when this PKA, after being knocked on to by the neutron, it can actually knock onto other iron atoms, and this primary knock-on atom knocks onto this other iron atom, And this can cause a secondary knock-on effect. Secondary knock-on. Because it's not being kinetic energy is not being imparted to it via a neutron, but rather a PKA. So this is what we call a secondary knock-on atom, or SKA. You can see with so much energy in this single PKA, we can cause a lot of SKAs to be created, a lot of secondary knock-on atoms. And this will actually cause a lot of a collision cascade. Now, every time an atom is dislodged or displaced, we actually make a Frankel pair. Frankel pair. And as we know, Frankel pair is actually a vacancy and interstitial. So when a neutron knocks onto an atomic lattice or metal lattice, we get a lot of vacancies plus interstitials. Now, of course, we'll talk more about this in the next video, and we will talk about how many vacancies and interstitials are being made, how many Frankel pairs are being made, or how many secondary knock-on atoms one primary knock-on atom, a PKA, can make. So that's all for this video. We'll talk more about it in the next video. And if you want to read more about it, you can check out the link I'll be providing below. A lot of this content which I'm talking about can be viewed in a PDF file. It's a book by Professor Olander in UC Berkeley. And yep, so yeah, that's all I have for you. Thanks for watching. I'll see you again. Bye bye.